I'm going to talk about the RoboCompanion proposal that deals with a slightly different domain, but essentially addressing the dream of developing a new generation of machines. The starting point is the analysis of what is around us. Technology, of course, we know, has made most heavy jobs lighter, faster, and more productive. But technology has a number of unfinished business. For example, the outsourcing of production that cannot be automated, or the low productivity in crucial sectors. For example, the medical, the health care sector is really a pride, but also a burden for Europe. We have to do better. And we have to reduce dangerous tasks that are still causing deaths and disabilities. There are very concerning, I would say, very heavy figures for this. Technology has made our lives safer, but still we are facing with natural man-made black swans like the Fukushima accident that is costing a huge amount of money. And technology has freed us from many home chores, but at the same time, there is, I like this figure very much, I must say. I'm sure all of you will like this. That shows the problem we still have to have a, say, more relaxed life, all of us. And we have a productivity challenge. It has been said due to a very important result, that is life expectancy. But the problem is the ratio between retired and working people is rapidly increasing, so we need to dramatically increase the productivity of the working population. And we have a challenge. We know very well there is a mismatch between our problems and our aspiration. And the question is, can technology be a solution? This is a question that for many of us is as a natural answer, but not really for all people. So we want to keep the attention and the opinion of society very closely into account. Robotics is a good place to start to answer this question. Why? Because Europe is very strong in this. We are leaders in this. We are leaders in research, we are leaders in industry, undisputedly. We have more than 1 million operational industrial robots in the world with a growth of 6% per year. The reliability is impressive, 40,000 hours mean time before failure for industrial robots. It's impressive. Those are extremely dependable machines. So our technology is dependable, it's very strong. And the service robots market is exploding with the rate of growth of 14% per year. 6%, 14%, those are figures, real figures that count. And people love real robots. Real people love real robots. There's been a concern sometime about the acceptability of robots. I can tell you, this is really not true. People love real robots, from children, as you see in this figure, to elderly people. So they will accept useful solutions that work. There is a bottleneck in robotics, though. The more functionality we want, the more complexity, energy, computation, and cost we have to afford. And the system becomes less controllable, less efficient, less robust, and ultimately even less safe. So we have to deal with this bottleneck. And this is why, in a long-term perspective, our proposal corresponds to a sort of third wave that wants to build upon the strength of Europe in this field and to build the future. So we need an all-new robotics, we say, still building on what we know. So we need simplification mechanism, new materials, fabrication technology, new energy forms. This is really what we want. Really the scientific goal of robot companions could be said simplification. Understanding the secrets of nature that does this regularly. And to transfer this into the design of and fabrication of an entirely new generation of machines. This is why we want to tap the biggest and most advanced treasure of engineering solution, looking at nature, studying natural organisms, understanding what makes them so smart and efficient, studying things only living organisms can do and how they do it. And all this is summarized in our grand scientific challenge, the unifying scientific challenge that we are going to address. That is, to unveil the natural principles of complexity, morphological computation, and sentience, and to translate the resultant scientific knowledge into design principle and fabrication technology for robot companions that effectively and safely act, interact, and adapt to their physical and social environment. You understand that all these words, keywords, are very, very carefully really are the result of a lot of thinking, a lot of elaboration, and are really our dream. I think we can see now a short video.
We share this planet with 7 billion people who have achieved great welfare, and we will get older than any generation before us. This welfare faces challenges in our private, economic, social and natural environments. Humans have overcome previous challenges by using tools and technology, but current technology cannot offer what it takes to assist us now and in the future to create sustainable welfare. To find sustainable welfare, we must develop a new technology to assist us in living and aging while remaining active, independent and creative. We need a new generation of robots that can answer our human needs and interests, support us and our environments, and become an active part of our world. We need robots that are aware of us and themselves, robots that can integrate perception, cognition, emotion and action. We call this sentience. To achieve sentience takes more than technology. Evolution progresses by the conservation of principles. Principles as morphological computation and complexity have been preserved in bodies and brains, giving rise to sentience. By investigating nature, we can thus understand, develop and integrate these principles into a new sentient technology for robot companions. Robot companions will have many applications, as universal lifestyle assistants, assisting us at home and when we need care, assisting us in our economy, in our cities, assisting us in maintaining the planet. We will develop robot companions at multiple scales, from micro and meso to macro and human compatible. We envision the development of robot companions as the start of an entirely new class of technology. Current robots are specialists, based on mechatronics using machine vision, machine learning. But despite the achievements, this is not enough. Robot companions will federate these efforts, broaden them, boost them, and give them a common goal. The quest for robot companions will drive unprecedented levels of collaboration, including material science, robotics, neuroscience, and including sociology, ethics and law. It will fuel the development of a new science of embodied sentience. Conversely, building robot companions and integrating them in society will validate the scientific principles on which they're based, leading to a new synergy between science and engineering. Robot companions will integrate across its stakeholders. Science, industry and society must come together to be able to successfully develop and deploy future robot companions. Sentient robot companions are more than science, more than integration and more than applications. They are more than mechatronics, more than robotics. Robot companions is more than future.
This is how we want to implement this vision, with this bridge that links science to application, through a number of steps: scientific pillars, new engineering principles, deployable platforms to address this social problem of the sustainable welfare. The first scientific, all of these pillars, by the way, are new concepts. I mean, new doesn't mean entirely new, but novel at the international level, distinguishing and featuring European research. Nobody is doing this in the world at the same level of depth. First pillar is simplexity, that comprise a collection of solutions that we call the simplification mechanism that can be found in living organisms. And this approach copes with the real world and to coordinate a large amount of motor and sensory data. And we can recognize a number of principles that we are going to investigate, like inhibition, disinhibition, selection of information reduction, probabilistic anticipation, complexify to better simplexify, cooperation and redundancy, and meaning. And those are examples of how simplexity materializes into behaviors, like in this case, grasping or just walking. The second scientific pillar is morphological computation, that essentially, you can read the definition, aims at canceling the distinction between control and the thing that we want to control and the controller. So essentially falls apart. This by addressing and making use of the shape and the material of a system. You can see this is a behavior. You see very robust behavior of a very simple mechanism making use of reflexes. This is essentially a very simple control, but with a deep understanding of the mechanism of the machine. This means simplifying eventually, and this is something that happens also here in the case of a gripper. You know, we are able to do very sophisticated multi-fingered hands, but we can get the same result of grasping different objects with a smart use of shape and material, like in this case. So those are the kind of, if you wish, a translation of what we learn from the simplexity principle, scientific principle, into more engineering design principles aimed at simplification, robustness, ultimately low cost. This is extremely interesting for industry, by the way. The third scientific pillar is sensing. That is the integration across perception, affect, cognition, and action. Is the creation of a coherent scene in which action can be interpreted, predicted, planned, generated, and communicated. And here, there is a very deep and intense cooperation with the community of neuroscience. And there are a number of principles shown here. How science is grounded in instantiated self, is enacted in sensory motor coupling, is maintained in the coherence between sensory motor prediction on the agent, and combines high levels of differentiation with high levels of integration. And you see here an example of what sensing can be. Actually, we do not have sensing machine today, only sensing organism. This is what we want to capture, these secrets. The fourth scientific pillar is the multifunctional nanomaterials and energy. Here is how we want to translate these principles into the body of these new robots, using new materials with a number of functionalities, new forms of power storage, harvesting, and generation, and eventually achieving our objective of compliance, computational load, high energy efficiency, ultimately low cost. And we have a number of key principles that will be explored from integrated design to energy harvesting. And dealing with roadmaps. Here you can read the kind of roadmaps we want. Even if I have to say, in our flagship proposal, we have a very limited number of roadmaps. You know, actually, we want to favor disruptive innovation with no roadmaps, the things that we cannot predict. So we really want to have roadmaps, but also to encourage creativeness and disruptive new ideas in our environment. Society is a pillar, is a fundamental part of our activity. We want to understand societal needs, attitude, and expectation, to develop ethical, legal, and societal principles, to design educational programs, to involve policymakers, stakeholders, member states, and industry, according to key principles like the Charter of Fundamental Rights of the European Union. So we will address a lot of attention to this. So overall, you see, our vision is like this: science-grounded robotics, society, scientific pillars, new science, new engineering, new platforms, new industry, new market, new jobs, in addition to the ones we have. And the work program is built like this. So societal needs drive the design of platforms. The platforms indicate science and technology requirements, scientific pillars, then are developed through a number of work packages, if you will, addressing each specific scientific and technological topic, so developing the new technology for the societal needs. And just to give you a practical idea of what we can proceed, we will proceed in two ways, essentially. One, the top row, is starting from existing platform and replacing components with novel ones. That is, taking advantage of the strength of Europe in this field and providing intermediate results at month 30 and ultimate results at year 10. The second is to start immediately from novel approaches, like the octopus, for example, to develop entirely new components and subsystems, also with intermediate results. And those are practical, concept, of course, because we cannot predict the future. And those are concepts of what can ultimately come. And of course, robots will be integral part of the emerging cloud. They will not be totally autonomous. They will have strong connection with the net. Basic principle, scientific excellence is fundamental, leadership, openness, metrics, measurability, and a number of other concepts that will be translated into a detailed governance model that is shown here that essentially links the CPCSA part with the ERANET part. And obviously, we have a huge number of colleagues participating. The consortium at this time includes 20 leaders, 42 co-leaders, 44 institutions from all over Europe, and a number of supporting partners from all over the world, including number of industries. What is important to note is that most of those industries are not robotics industry. And I'm going to conclude. Of course, the scientific robotic community strongly supporting our proposal. This is going to be, this is considered to be a truly global initiative. And just to conclude, let's think to the possible impact of what we are talking. The case of the housekeeper robot. 10% of European households buying a very useful robot. You remember the ironing mountain for the cost of a car. This means an industry of the same size as the automotive one. And so we believe it's time to put Europe in pole position, because Europe knows how to build robots. We have a reputation. We know. We are worldwide known for this. And this is a realistic dream, because we want to make these complex and demanding tasks so easy that you do not even realize you are doing them. Robot companion could become transparent, non-invasive, just like computation, from PC to POs, personal operators. And this is my final slide. And this is our dream, and I think is what we need And I think that everybody will subscribe this kind of vision, I think. Thank you very much.